The Dragonfire weapon marks a revolutionary change in modern air defense by replacing traditional ammunition with pure directed energy, fundamentally altering how threats in the sky are neutralized. Instead of firing missiles or shells, Dragonfire projects a high-energy laser beam that can be focused onto a target with extraordinary precision. This beam heats the surface of a drone or aerial vehicle in a matter of seconds, melting key components, damaging sensors, or causing structural failure until the target is no longer able to fly. Because the laser travels at the speed of light, there is no lead time or ballistic calculation needed, making Dragonfire especially effective against fast-moving and highly maneuverable drones that would normally be difficult to intercept using conventional weapons. One of the most important aspects of this system is its accuracy. Dragonfire can reportedly strike a target the size of a coin from significant distances, which means it does not rely on explosive force to destroy threats. This precision allows operators to disable drones cleanly, without the risk of debris scattering over a wide area. In modern conflicts, where drones are often used close to friendly forces, civilian areas, or valuable infrastructure, such controlled engagement is a critical advantage. The ability to apply just enough energy to neutralize a target, rather than obliterate everything around it, reflects a new philosophy in warfare focused on efficiency and control. Another defining feature of Dragonfire is the dramatic reduction in cost per engagement. Traditional air defense missiles can cost hundreds of thousands, or even millions, of dollars per shot, making them impractical against cheap, mass-produced drones. Dragonfire changes this equation completely. Each laser shot costs only the price of the electricity required to power the beam, often described as equivalent to running a household appliance for a short period. This allows armed forces to defend against large numbers of incoming drones without worrying about exhausting expensive missile stocks or draining defense budgets. In an era where drone swarms are becoming a real threat, this cost efficiency could be as important as the weapon's destructive power. The speed of engagement is another crucial advantage. Since the laser does not need to physically travel like a missile, Dragonfire can engage targets almost instantly after detection. This enables rapid retargeting, allowing the system to switch from one drone to another in quick succession. In a scenario where multiple drones are approaching at the same time, this ability could mean the difference between a successful defense and an overwhelmed air defense system. Traditional systems often struggle in saturation attacks, but a laser weapon with a deep power supply can continue firing as long as energy is available. Dragonfire also represents a technological step forward in how future battlefields may look. As more militaries adopt drone technology for reconnaissance, strikes, and psychological warfare, defenses must evolve just as quickly. A laser-based system signals a shift toward directed energy weapons as a core part of air defense, rather than a supporting role. While Dragonfire does have limitations, such as reduced effectiveness in bad weather or heavy smoke, its successful testing shows that these challenges are being addressed through improved sensors and targeting systems. Overall, Dragonfire demonstrates how advanced laser technology can redefine the balance between attack and defense. By combining precision, speed, and extremely low operating costs, it threatens to undermine the advantage that cheap drones once offered on the battlefield. While it does not make every drone obsolete, it significantly raises the risk and cost for anyone relying on drones as a primary weapon, marking a turning point in modern military defense systems. One of the most important reasons Dragonfire is seen as a game changer is its ability to defeat modern drones at a fraction of the cost and time required by traditional air defense systems. In recent conflicts, drones have become attractive weapons because they are cheap, disposable, and easy to deploy in large numbers. Militaries have often been forced to respond to these low-cost threats with extremely expensive missiles, creating an imbalance where defense costs far more than attack. Dragonfire directly targets this weakness. By using a high-energy laser powered by electricity, each engagement costs only a small amount compared to the massive price of interceptor missiles. This changes the economics of warfare. Defenders are no longer punished financially for shooting down cheap drones, and attackers lose the advantage of overwhelming defenses through numbers alone. The laser's speed further strengthens this advantage, as it strikes targets at the speed of light with no travel time, allowing rapid engagement of multiple drones in quick succession. This makes Dragonfire especially effective against swarm attacks, where dozens of drones approach simultaneously to confuse or saturate defenses. Instead of choosing which targets to intercept and which to let through due to limited ammunition, operators can continuously engage threats as long as power is available. This ability fundamentally shifts drone warfare from a numbers game back toward controlled defense, making drone attacks far riskier and less reliable. Another key point is how Dragonfire represents a broader technological shift toward precision and control in future warfare. Unlike explosive weapons, laser systems apply energy only where it is needed, reducing unintended damage and increasing operational flexibility. This precision is especially valuable in naval and coastal defense, where warships may need to defend themselves in crowded sea lanes or near civilian infrastructure. By burning through a drone's sensors, wings, or control surfaces, Dragonfire can neutralize threats without causing large explosions or falling debris over wide areas. This controlled method of engagement reflects how modern militaries are adapting to complex battle environments where political, civilian, and strategic considerations matter as much as pure firepower. Dragonfire also signals the rise of directed energy weapons as a permanent part of military arsenals rather than experimental systems. While weather conditions, line of sight, and power generation still place limits on laser weapons, continued testing and development show these challenges are being reduced. As sensors improve and power systems become more efficient, laser defenses are expected to grow stronger and more reliable. In this context, Dragonfire is not just a single weapon but a preview of how future air defense will operate. It forces drone developers to rethink designs, tactics, and materials, while giving defenders a scalable, sustainable way to protect ships and bases. Together, these changes explain why Dragonfire is seen as a major threat to the effectiveness of drones and a turning point in the evolving balance between attack and defense. The first major point behind the impact of Dragonfire is how it reshapes the cost and effectiveness balance between drones and air defense. For years, drones gained dominance because they were cheap, easy to replace, and could force defenders to waste extremely expensive missiles. This imbalance encouraged the use of drone swarms, where even if most drones were shot down, the attacker still achieved success by exhausting the defender's resources. Dragonfire directly challenges this logic. By using a laser powered by electricity, the cost of shooting down a drone drops to a negligible level compared to missile-based systems. This allows defenders to engage every incoming threat without hesitation, removing the painful decision of whether a target is worth an interceptor. Over time, this undermines the strategic value of mass drone attacks, because the economic advantage shifts back to the defender. When attackers realize their drones can be neutralized cheaply and repeatedly, the entire appeal of using large numbers of disposable drones begins to fade. The second key point is Dragonfire's precision and speed, which introduce a new level of control in air defense operations. Traditional weapons rely on physical projectiles that must travel to the target, creating reaction delays and the possibility of misses or collateral damage. Dragonfire's laser, however, engages at the speed of light, meaning once a target is detected and locked, the engagement is almost instantaneous. This is especially important against fast or maneuvering drones that can change direction suddenly. The laser can remain focused on critical components, such as sensors, motors, or wings, until the drone fails. This precision reduces the risk of unintended damage, which is vital in modern combat environments where operations often take place near civilian infrastructure or friendly forces. The ability to disable rather than explosively destroy targets also gives commanders more tactical options. Instead of relying solely on brute force, Dragonfire supports a more measured and controlled form of defense that aligns with modern rules of engagement and political constraints. The third key point lies in what Dragonfire represents for the future of warfare rather than just its immediate battlefield performance. This weapon signals a broader shift toward directed energy systems becoming a standard part of military arsenals. While lasers have existed in experimental forms for decades, Dragonfire demonstrates that the technology has matured enough for real-world deployment. This has long-term consequences for how both attackers and defenders plan their strategies. Drone designers will be forced to rethink materials, flight profiles, and tactics to survive laser engagement, increasing complexity and cost. At the same time, defenders gain a scalable solution that can evolve as power generation, sensors, and tracking systems improve. Although Dragonfire still faces limitations such as reduced effectiveness in poor weather or heavy smoke, these constraints are well understood and actively being addressed through technological advancements. Over time, these improvements will likely make laser defenses more reliable and widespread. Together, these 3 points explain why Dragonfire is viewed as a serious challenge to the dominance of drones in modern conflict. It attacks the economic advantage of drones, introduces unmatched precision and engagement speed, and marks a turning point in military technology toward sustainable, energy-based defense systems. While drones will not disappear entirely, their role and effectiveness are being fundamentally questioned. Dragonfire does not end drone warfare, but it forces a major evolution in how drones are built, deployed, and countered, signaling a new phase in the ongoing competition between offensive innovation and defensive adaptation. The first key point is how Dragonfire completely alters the economic balance of modern drone warfare. For years, drones have been effective largely because they are cheap and expendable, while the systems used to shoot them down are often extremely expensive. This imbalance allowed attackers to drain defenses by forcing them to use high-cost missiles against low-cost targets. Dragonfire breaks this cycle. Because it uses a laser powered by electricity, each engagement costs only a small amount compared to traditional interceptors. This means defenders no longer hesitate before firing and no longer face the risk of running out of costly ammunition during prolonged attacks. Over time, this removes one of the biggest advantages drones had on the battlefield and makes large-scale drone attacks far less attractive as a strategy. The second key point is Dragonfire's unmatched precision and engagement speed. Traditional air defense weapons rely on physical projectiles that take time to reach their targets and can miss due to evasive maneuvers or environmental factors. Dragonfire's laser, by contrast, strikes at the speed of light. Once a drone is detected and tracked, the laser can be focused instantly on a critical point, such as a wing, sensor, or propulsion system. This precision allows the weapon to disable drones rather than relying on explosive destruction. In modern combat environments where forces often operate near civilians, ports, or vital infrastructure, this controlled method of engagement is a major advantage. It reduces collateral damage and provides commanders with a tool that aligns better with strict rules of engagement and political constraints. The third key point is Dragonfire's effectiveness against saturation and swarm attacks. Drone swarms have become a favored tactic because they overwhelm traditional defenses, which have limited ammunition and slower reload times. Even advanced missile systems can struggle when faced with dozens of incoming targets at once. Dragonfire addresses this challenge by allowing rapid retargeting. As long as power is available, the system can engage one drone after another without the need to reload or resupply physical ammunition. This sustained firing capability makes it far more difficult for attackers to overwhelm defenses through sheer numbers. While no system is completely invulnerable, Dragonfire significantly raises the threshold required for a successful swarm attack, forcing attackers to invest more resources, coordination, and complexity to achieve the same effect. The fourth key point is what Dragonfire represents for the future of military technology and doctrine. Beyond its immediate performance, it signals the arrival of directed energy weapons as a practical and deployable solution rather than an experimental concept. This has long-term implications for both offense and defense. Drone designers will need to adapt by using new materials, flight profiles, or tactics to reduce vulnerability to lasers, which increases costs and technical difficulty. At the same time, defenders gain a scalable and upgradable system that can improve as power generation, sensors, and tracking technologies advance. Although Dragonfire still has limitations, such as reduced effectiveness in bad weather or obscured visibility, these challenges are well understood and actively being addressed through ongoing research and development. Taken together, these 4 points explain why Dragonfire is viewed as a serious disruption to drone-based warfare. It undermines the economic logic of cheap drone attacks, delivers unprecedented precision and speed, counters swarm tactics more effectively, and marks a broader shift toward energy-based defense systems. Drones will not disappear from the battlefield, but their dominance is being challenged. Dragonfire forces a rethink of how drones are used and how air defenses are designed, signaling a new phase in the evolving balance between attack and defense in modern warfare. The first key point is the way Dragonfire changes the cost equation that has favored drones for so long. In modern conflicts, drones are attractive because they are inexpensive, easy to replace, and can force defenders to spend far more money shooting them down than the drones themselves cost. This imbalance has allowed attackers to exhaust air defense systems by launching repeated low-cost attacks. Dragonfire directly challenges this advantage by using a laser powered by electricity, making each engagement extremely cheap compared to missiles or gun-based interceptors. Defenders can now respond to every incoming drone without worrying about wasting valuable resources, which removes one of the main strategic benefits of drone warfare and makes sustained drone attacks far less effective. The second key point is Dragonfire's extreme precision and speed, which set it apart from conventional air defense weapons. Because the laser beam travels at the speed of light, there is no delay between firing and impact. Once a drone is detected and tracked, the laser can be focused on a very small point, heating and damaging critical components until the drone fails. This precision allows the system to disable targets without relying on explosive force, reducing the risk of collateral damage. In environments such as naval operations, ports, or areas close to civilians, this controlled method of engagement is a major advantage. It gives commanders more confidence to use the system in complex situations where traditional weapons might be too risky. The third key point is Dragonfire's ability to counter saturation and swarm attacks, which have become one of the most dangerous uses of drones. Traditional air defense systems have limited ammunition and can be overwhelmed by large numbers of incoming targets. Drone swarms exploit this weakness by forcing defenders to choose which threats to intercept and which to let through. Dragonfire addresses this challenge by eliminating the need for physical ammunition. As long as power is available, the system can continue firing, rapidly switching from one target to another. This sustained engagement capability makes it much harder for attackers to overwhelm defenses through sheer numbers, raising the cost and complexity of successful drone swarm tactics. The fourth key point is how Dragonfire strengthens naval and fixed-site defense. Warships and military bases are increasingly threatened by drones used for surveillance, targeting, and direct attack. Installing a laser-based defense system provides a layered defensive option that complements existing missile and gun systems. Dragonfire can be used against smaller, cheaper threats, preserving expensive missiles for more dangerous targets such as aircraft or cruise missiles. This layered approach improves overall defensive resilience and ensures that high-value assets are protected more efficiently. For naval forces in particular, where resupply at sea is limited, a system that relies on power rather than ammunition is especially valuable. The fifth key point is what Dragonfire represents for the future of warfare and military doctrine. Its successful testing shows that directed energy weapons are moving from experimental projects to practical, deployable systems. This shift will influence how future conflicts are planned and fought. Drone developers will be forced to adapt by using new materials, tactics, and technologies to survive laser engagement, increasing costs and reducing the simplicity that once made drones so appealing. At the same time, defenders gain a scalable and upgradable solution that can improve as power generation, sensors, and tracking systems advance. Although Dragonfire still has limitations, such as reduced effectiveness in poor weather or obstructed visibility, these challenges are being actively addressed. Together, these 5 points explain why Dragonfire is seen as a major threat to the dominance of drones in modern warfare. It undermines their economic advantage, delivers unmatched precision and speed, counters swarm tactics, strengthens layered defense, and signals a long-term shift toward energy-based weapons. Drones will continue to exist, but systems like Dragonfire force a fundamental rethink of how they are used and defended against on future battlefields. The first key point is how Dragonfire fundamentally destroys the cost advantage that made drones so powerful in modern warfare. For years, drones have been effective not because they were unstoppable, but because they were cheap. Attackers could launch low-cost drones and force defenders to respond with extremely expensive missiles, creating a situation where defense was financially unsustainable. Dragonfire reverses this imbalance. Because it uses a laser powered by electricity, each shot costs very little compared to traditional air defense weapons. This allows defenders to engage every incoming drone without hesitation, removing the economic pressure that once favored drone attacks and making repeated strikes far less attractive. The second key point is Dragonfire's speed and precision, which redefine how air defense engagements occur. Unlike missiles or gunfire, which take time to reach a target and can be affected by gravity or evasion, a laser strikes at the speed of light. Once a drone is detected and tracked, Dragonfire can focus its beam instantly on a critical point, such as sensors, wings, or propulsion systems. This precision allows the weapon to disable drones efficiently rather than relying on explosive destruction. In modern combat environments where operations often take place near civilian areas, ports, or vital infrastructure, this controlled engagement significantly reduces the risk of collateral damage. The third key point is Dragonfire's effectiveness against drone swarms and saturation attacks. One of the most dangerous uses of drones is launching them in large numbers to overwhelm air defenses with limited ammunition. Traditional systems can be exhausted quickly in such scenarios, allowing some drones to slip through. Dragonfire removes this weakness by eliminating the need for physical ammunition. As long as sufficient power is available, the system can continue firing and rapidly retargeting new threats. This sustained engagement capability makes it much harder for attackers to overwhelm defenses through numbers alone, forcing them to rethink swarm tactics entirely. The fourth key point is how Dragonfire strengthens layered defense strategies, especially for naval forces and fixed military installations. Warships, ports, and bases are increasingly targeted by small drones used for reconnaissance, targeting, or direct attack. Using expensive missiles against such threats is inefficient and unsustainable. Dragonfire provides a perfect middle layer of defense, allowing militaries to reserve missiles for larger threats like aircraft or cruise missiles while using the laser against cheaper, smaller targets. This layered approach improves overall defensive resilience and makes protection of high-value assets more efficient and sustainable over long periods. The fifth key point is Dragonfire's psychological and strategic impact on future warfare. Weapons are not only about destruction but also about deterrence. Knowing that drones can be detected and destroyed cheaply and quickly changes how adversaries plan attacks. The fear of losing entire drone fleets without achieving meaningful results reduces the attractiveness of drone-heavy strategies. This forces attackers to invest more in countermeasures, stronger materials, or complex tactics, increasing costs and reducing the simplicity that once made drones appealing. In this way, Dragonfire reshapes strategic thinking even before a shot is fired. The sixth key point is what Dragonfire represents for the future of military technology. Its successful testing shows that directed energy weapons are no longer experimental concepts but practical tools ready for deployment. While limitations such as weather, line of sight, and power generation still exist, ongoing improvements in sensors, tracking systems, and energy storage are steadily reducing these challenges. Dragonfire is not just a single weapon but a sign of a broader shift toward energy-based warfare. As this technology matures, it will likely become a standard part of air defense systems worldwide. Together, these 6 points explain why Dragonfire is seen as a serious threat to the dominance of drones. It removes their cost advantage, delivers unmatched speed and precision, counters swarm attacks, strengthens layered defenses, alters strategic thinking, and signals a new era of directed energy weapons. Drones will not disappear, but their role is being fundamentally challenged, marking a turning point in modern military defense.